Question 6a. Benzene, benzoic acid, and phenol. These three can undergo nitration, and the reagents and conditions they use they are different. So this question is a very good question because it's telling you the effects of electron donating groups and the electron withdrawing groups to the activities of the benzene or reactions of benzene. So let's look at table 6.1. What is the reagents and conditions used for the nitration? Of course, what is nitration? So this is a process to introduce the nitro groups into the benzene. So we call nitration. Nitro group means NO2. For the benzene, the reagents and conditions needed is the concentrated HNO3 and the concentrated HSO4, which is the catalyst, and the temperature is 50 degrees C. When a benzoic acid needs to undergo the same nitration, so it needs a harsher condition, a higher temperature, so it's not 50 degrees C, now it's 100 degrees C for this benzoic acid. Means it's relatively more difficult for benzoic acid to undergo nitration. For the phenol, the reagents and condition used is just a dilute nitric acid. No need to use concentrated acid. And the temperature is lower, is about 20 degrees C. So this information is telling us that phenol is the one that's more likely to undergo nitration and is easier. Why? So later we're going to compare this and explain. Okay, I'll tell you later. So for this one, the phenol, because we know that the OH group is electron donating, the lone pair on nitrogens will delocalize in the benzene ring. So it's going to have 2,4 directing. Means when the nitro groups approach the phenol, the nitro group will bond to 2, 4, 6 position. So this we call 2,4 directing. Means when there is nitronium ions or the electrophile that approach, it will go to these 3 position, right? So and form this the nitrobenzene. For this benzoic acid, we know that is electron withdrawing groups and is 3,5 directing. Means when there is a electrophile like the nitronium, so the nitronium will go for the 3 and 5 position. Means the electrophilic substitutions will happen at the 3, 5 position. Okay, so why? Later I'll tell you the reason. So the most important thing that you must know is when we have electron donating group, so it's 2,4 directing, and when we have electron withdrawing group, so it's 3,5 directing. So 2,4 directing and 3,5 directing is for the electrophilic substitutions. Okay, part 1. Complete figure 6.1 to shows the mechanism of the reactions between the benzene and the nitronium. So this benzene and nitronium is given. You need to draw the arrow from benzene ring, point to the nitrogen, because the nitrogen is the one that charged positive. After that, you need to draw this intermediate. So this intermediate, you should show the CH bond and the CN bond, means the carbon with this nitro group. So it shows that the new bonds form between the C and the N. After that, you need to draw one arrow from the CH bond to show that this CH bond break, and this pair of electrons will move into the benzene ring or move into the ring to restore the benzene ring. So eventually the hydrogen's ion will remove and the nitrobenzene will form. So means the nitronium here is going to substitute the hydrogen in the benzene ring. So eventually it forms nitrobenzene and this H plus will removed. So this is a substitution which caused by electrophile. So we call electrophilic substitution. Part 2. Write an equation to show how H2SO4 is regenerate. Because I already told you that H2SO4 is a catalyst, means it can be regenerated. So how to regenerate? Before you answer this question or you give this equation, you must first know this equation. When we use a concentrated nitric acid and concentrated H2SO4, when they react, it will form nitronium ion. At the same time, it will form this HSO4 negative, the hydrogen sulfate ion. So this anion will react with the H plus that's removed just now. So these two will combine and form back the H2SO4. So that's why the equation is like this. The HSO4 negative plus the H plus form back the H2SO4. Part B. Draw the major products for the mono nitration, just one nitro groups only. For the benzoic acid and phenol, I already told you phenol is 2,4 directing. So this is 1, 2, 3, 4. So when there is a nitronium ion or when there is an electrophilic substitution, so the nitro group will move or will go to the 2, 4, 6 position. The major products for this phenol it's better for you to put the nitro group at the 4th position because it's further away from this OH, is relatively more stable. For the benzoic acid, I already told you, is 3,5 directing. The benzoic acid, this COOH is 3,5 directing, means when there is a nitronium ion, so it will go to 3 and 5. So of course 3 and 5 is actually similar. So let's say now is 1, 3. So this is major products. So therefore you just need to draw these two structure. This is the comparison between the phenol, benzene and benzoic acid. Why? When they undergo nitration, phenol is much easier, benzene is moderate, and the benzoic acid is harder. So first, based on the tables, the previous table, you need to figure out which one is easiest undergo nitration, which one is more difficult to undergo or the most difficult to undergo nitration. So from the table we know that phenol just needs a dilute HNO3 and 20 degrees C. So therefore phenol is the one that easiest undergo the nitration. Followed by benzene, then benzoic acid is least easy. So this is a trend. So what is the reason to make this phenol easiest to undergo nitration? Means for it to react and form the nitrobenzene, reacts with the nitric acid and form the nitrobenzene. So there is a reason. These resonance structures you no need to draw, just to tell you what is the reason. For phenol, we know that the lone pair on oxygens will delocalize in the benzene ring, something like this. So one lone pair will move and get into this benzene ring, and as you can see, the benzene ring now has extra electrons or more electrons. So we say that the lone pair here, after it's delocalized in the benzene ring, is increase the electron density in the benzene ring and make this benzene ring more active. So we say that it activates the benzene ring. And as you can see, this is 1, 2, 3, 4, 5, 6, all the position. So as you can see, the position 2, 4, 6 is always the one with the lone pair or negative charge. So therefore, these are the place that will attract the electrophiles easily. So the electrophile is the nitronium ion or this nitric acid. So therefore, it's always direct 2, 4, 6 position. That's the reason why. For the benzoic acid, why is the least easy to undergo nitration? Because the COOH is electron withdrawing groups, something like this. So means if you try to get electrons from benzene ring, as you can see, one pair of electrons from benzene ring move up, okay, and eventually form this first resonance structure. And of course, it will these electrons or this pair of electrons will move, and eventually the charge positive will change. So as you can see from this resonance structure, after the electron movement and form this the resonance structure, so the charge positive is actually at this 2, 4, 6 position. So means this 2, 4, 6 position will not really attract electrophile. So therefore, for this benzoic acid, it has no choice. It must use the 3 and 5 positions for the nitration, because these are the place that no charge positive, easy to attract the electrophile. So that's why we say that the COOH, this group is electron withdrawing. It reduces the electron density of benzene ring and deactivate the benzene ring. That's the reason. So if you understand what I'm telling you now, so you should be able to understand the explanation. So why phenol is the one that easiest undergo nitration? So because the lone pair on oxygen delocalize into the ring, and after it's delocalized, it will increase the electron density of the ring, make it easy to attract the electrophiles. So in this case is the nitric acid. So why the benzoic acid is now least easy? Because the carbonyl group in the benzoic acid is electron withdrawing. So as you can see here, okay, it's get electrons, and therefore the electron density in the ring now decreases. So we say that now the benzene ring is get deactivated, and therefore it makes it least easy to undergo nitration. So that's the reason why. Now next part. Part D. So we have the figure 6.2 here, which is a few steps. Okay, so it's a 3 steps reaction. So let's start with the first one. So we have this compound, the 2 benzene ring with the 2 nitro groups. and this compound undergoes step 1, and of course this is what I put, so initially it's blank. So you need to deduce a structure from this molecular formula. Okay, so therefore, the first step that you need to do is you need to get the molecular formula for the first compound. So the benzene ring here is C6H4. This one also C6H4. So now we have a 2 nitro group. Therefore, the molecular formula is this C12H8N2O4. So compare this one with the X, the molecular formula of X. So you will know is actually remove 4 oxygen and add 4 hydrogen. So from this comparison is very clear, which means the 2 nitro groups here will undergo reduction and form the phenylamines. So means remove 2 oxygen, add 2 hydrogen, add 2 hydrogen. That's a reaction. So step 1 is the reductions of the nitrobenzene. Now, after that, the compound X, so you can draw something like this, the 2 phenylamines, right? After that, after step 2, then it will form Z. So this one, you need to, of course, later you have to deduce from the azo die here, this conglomerate. So the Z here, after X form the Z will further react with Y. So Y now is having this molecular formula C10H8NO3SNA. So before you deduce this Y and Z the structure, so you have to analyze the structure, this azo die structure. So from this dice molecule or this structure, we know that there are 2 azo link here, 2 azo link, and this 2 azo link is telling us that the structure means the diazonium structure is here, this one. So means this die is actually formed from the benzene diazonium ion, okay, something like this. So it have 2 benzene diazonium ion, right? And these are the 2 groups that reacts with the benzene diazonium ion. So this is how you analyze and get the correct structure. So now we are quite sure this part is from the Z. So Z will form this one. So now we know that the phenylamine must undergo diazotization to form this diazonium ion. Because once it's formed diazonium ion, it can form this azo die. So you just need to put this NN triple bond with a charge positive on nitrogen. Okay, this side also same. Okay, after that you can deduce the Y. So you just need to use this part. So if you count this part, so you get C10H6NO3SNA. So which is 1 hydrogen different from this Y. Okay, there is a reason, because when this benzene diazonium ion reacts with Y, So it's actually used this part and this part. So I show you the two reaction, how it can be done. So this one is the phenylamine. We know that phenylamine, this is electron donating group. So it will direct 246. So it seems like this what I call electrophilic substitution, it has no choice. So it must use this position. So one pair of electrons from the benzene ring, so we'll form new bondings, okay, with this N and this pi bonds break. So it will form the azole ring later, and this one will do the same thing. This position 1 2 second position, right? So one pair of electrons from benzene ring, okay, will move to this nitrogen, form a new bonding, CN bond, and pi bonds break. So this one is similar to the electrophilic substitutions that you learn. Means after this Y reacts with Z, one of the hydrogens here, this hydrogen will get substituted, and same as this hydrogen. That's why the Y here and this part, their difference is one hydrogen. So we are quite sure this part, okay, is from the Y. So we just need to draw the structure, the Y, based on this, right? So something like this. So we can get the full structure. So another Y, of course, here, this one, we'll use for the bonding to form this. This is another Y. So this structure is quite complicated, and I hope you know what is happening and how it reacts. So basically it's the electrophilic substitutions reactions between the phenylamine, means the Y here, with the benzene diazonium ion, okay, in the Z, right? So it has two electrophilic substitution, or actually two coupling reaction, right? So this one and this one, right, with the benzene diazonium ion. Okay, part 2. This part is quite easy because it's just reagents and condition. For the step 1, what is the reagents and condition needed? Okay, go back to step 1. Step 1 is the reductions of nitrobenzene. So we know that we must use the hot, thin, and concentrated HCl. So this is the reagents and the conditions needed, okay, for the phenylamines formation from the nitrobenzene. And do not forget to put this one, followed by sodium hydroxide solution. Why? Because when we use acid as the reagent, so this one at the end, the phenylamine, once it's formed, means this one, it will react with the HCl. So we don't want this to happen. We don't want the phenylamines to react with acid. Therefore, we need to use the alkalines followed by the sodium hydroxide solution. Make sure the phenylamines will form. Make sure the acid is not really there to react with the phenylamine. Step 2. So step 2 is this one. From this phenylamine, these two phenylamine, form these two benzene diazonium ion. So we need to use this one, sodium nitrite and the HCl. Condition is below 10 degrees C, let's say 5 degrees C. Why we want to use sodium nitrite and HCl? Because sodium nitrite and HCl once they reacts, they will form this nitrous acid. And this nitrous acid is the one that will form the benzene diazonium ion from this phenylamine. So that's why we need to use the sodium nitrite and HCl to let this HNO2 to form in situ during the reaction. So after that, with the help of acid, the HCl, and the presence of HNO2, then the phenylamine can form the benzene diazonium ion. So that's why we use this one. Okay, that's all. Thank you. I hope you understand.